All right, we're going to look at a review of the topic of continuity. So these would be some typical questions that you'd find on an AP test. As a matter of fact, several of them I probably did pull right from past AP exams. And the other ones are similar to those. All right, let's review the three-part continuity test. As you can see on this worksheet, there are 4 problems. And we're going to do one together as a model. So I think we're going to pick number 2. The question is the function f of x continuous at the break x equals 0? Use the definition of continuity of the 3 parts to justify your answer. All right, well, we know by itself, this piece right here, 1 minus 2 sine x, for every x value that's less than or equal to 0, it's continuous. So there's no concern about this graph being discontinuous anywhere on its restricted domain. And likewise right here for this exponential function, it's always continuous as well, even on its restricted domain. So that's why we're looking at just the behavior, the bad behavior that's occurring at x equals 0. All right, so let's do the 3-part continuity test. The first question is, the first part is the function defined at 0? Is there a functional value? Well, I look at the 2 restrictions and I go, well, this one has the or equal. So that means that x equals 0 belongs to this piece right here. So yeah, it's going to be defined. So plug in 0 to the appropriate piece. Perform the computations. So sine of 0 is 0. 0 times 2 is 0. So 1 minus 0 is just 1. Okay, so now we know that the point 0, 1 is on the graph. Let's see if the limit exists. So all I'm going to do is I'm going to plug in 0 to the top piece and plug in 0 to the bottom piece. And we're going to see if those 2 values are equal. I'm actually going to come over here and show the two limits, the left-hand limit and the right-hand limit. All right, let's look at the limit of the function as x approaches 0. I'll just start with the left. Numbers to the left of 0 would be smaller, so that would be this inequality, so it's going to be this piece right here. So we want to put the appropriate limit, the left or right-hand limit, with the appropriate piece. All right, we already found this. So we know that this answer is 1. Let's do the right-hand limit. So if I'm approaching 0 from the right, that means the number's bigger. So bigger than means the inequality greater than. Let's plug in 0 everywhere we see x. So e to the negative 4 times 0, or just 0, and e to the 0 is 1. Okay, so I'm going to try and squeeze it down here that because I've looked at the left-hand and the right-hand limit, and I have the same y values, that the limit exists. So that stack of 3 dots just means therefore. Therefore, the limit as x approaches 0 of f of x, let me see, yeah, it's called f of x, is equal to 1. All right, we're going to try and show all our work from far left to the far right. Okay, so the third part says, okay, consider part 1 and 2. Are they equal? Well, yeah, they are. We can see they are. So we know the graph is going to be continuous at x equals 0. But we need to show that notation. So we're using appropriate notation. We can say that f of 0, which I know is equal to 1, is also equal to this limit notation. They're both equal to 1, so I can set them equal to each other. That's all we're saying. All right, and to kind of wrap it up, because the question is the function continuous? I'm going to put another stack of 3 dots, therefore, and just respond to the question. F of x is continuous at x equals 0. Okay, well, this should serve as a good example of the 3-part continuity test. There are 3 more problems on this first part right here. And I think if you attempt them, you'll be fine. We can discuss anything that needs to be discussed at a later time. All right, let's move to the continuity part 2 worksheet. So I'm just going to scroll because it's all in the same document. So find your part 2 AP review continuity. Okay, so I've chosen a few problems on this worksheet to do together. So we're going to do number 1 first. All right, so we need to find out what the constants for a and b need to be so that this function is continuous on the entire real number line. Okay, so right now we can see that the y's are 24 when x is less than or equal to -7, so we have a horizontal line for x values less than -7. Then we have a line that's going to connect, hopefully, to make it continuous with with y equals 24. And then after it quits being a linear function between -7 and 9, after 9, then it becomes a horizontal line again, or array. All right, so what we have to do is find limits, find constants a and b such that the following function is continuous. What's similar to finding a and b so that the following function has a limit that exists at x equals -7 and x equals 9. So that's the interesting behavior. So let me get started. Okay, the first thing we're going to look at is at x equals -7. The graph has to match up. Okay, so let's involve the three-part continuity test. So does the function exist at -7? Sure, there's an or equal to that includes the -7, and it's going to actually be 24. Okay, let's find the left and right-hand limit at x equals -7. So we're practicing good notation too. As x approaches -7 from the left, number smaller than -7, that would put me on the piece that's y equals 24, so the left-hand limit is 24. Okay, let me look at the right-hand limit. As x approaches -7 from the right, number's bigger than, that means this inequality of ax plus b. I'm going to insert -7 for x. So I'm going to have a right-hand limit of -7a plus b. Okay, so therefore, for the limit to exist, the left-hand limit 24 must equal the right-hand limit -7a plus b. Okay, well, that's as far as we can get at x equals -7. The third part of the continuity test just says that part 1 and 2 must be equal. Well, it's like restating what we have here. It's saying that f of -7 must equal this limit right here of -7a plus b. So if you wanted to write it again, I mean, that's all we're doing. But we can't solve this because we have two unknowns and only one equation. Okay, but that's why we have three pieces. So let's do the same thing at x equals 9. Let's involve the three-part continuity test. Is the function defined at 9? Yeah, well, 9 belongs to the bottom piece because that's the or equal to. So that's -24. Okay, and then let's explore the left-hand limit and the right-hand limit as x approaches 9. 9 from the left, numbers smaller than 9 would put you on the linear piece. Remember, this is x is approaching 9, so where we see x, we're going to plug in 9, so I'm going to have 9a plus b. The right-hand limit, as I approach 9 from the right, numbers bigger than 9 would be this inequality, and that's -24. So if the limit's going to exist, it has to be that the left-hand limit, 9a plus b, is equal to the right-hand limit, -24. Okay, so for the third part of the three-part continuity test, I mean, it's just restating this again, that part 1 must be equal to part 2. So -24 equals 9a plus b. Is it necessary? No. Okay. Now to finish solving this, let's see if I have a little bit more space here, which is good. Okay, I have two equations with two unknowns. It's just a system of equations. You can use substitution method, elimination method. I think I'm going to take these two equations and use the elimination method. I'm going to try and get rid of b's first. So coming down here, I'm going to stack them on top of each other. And revisiting our algebra 2, the elimination method, I'm going to take and multiply the bottom equation by -1. So all the signs change, hopefully, and then I'm going to add down. So the sum here is -16a. These will cancel. This is equal to 48. Dividing both sides by -16, so a is -3. Need a little more working room. Okay, so the next thing I'm going to do is I'm going to find b by plugging a, -3, back into either of these two equations. So I'll just work with this equation right here. I'm going to add 27 to both sides, and that's going to turn that into 3. So a equals -3 and b equals 3. And that would certainly force this piecewise function to be continuous at its breaks. I think we're going to skip around and we're going to look at number 4 together. So you might want to pause, read the problem, kind of get your mind around what's being asked, and then restart the video. Okay, so h is the function given by these two pieces where a and b are constants. Oh, well, look at that. They went ahead and gave us what a and b's values are. I don't know why they didn't just plug them in the first place. Okay, probably just to make sure and have you pay attention to the fact that those are constants. Okay, so it tells us what a and b are, and then it says to us, the question is h of x continuous for all x's, in the interval from 1 to infinity? Well, notice that this piecewise function is only defined for values from 1 to infinity, so that's probably just a way for them just to restate that that's the domain. That's all they're doing. All right, so we have to use a 3-part continuity test. I think what I'm going to do is come over here, and you might want to too, is I'm going to rewrite this piecewise function with the appropriate a and b values. All right, so first of all, we start out with an absolute value piece, and then we change over to a quadratic. So we just want to see if they line up at the same y value. Let's see, a was what, -1, so -x squared, that's a downward opening parabola. B is -4, so that makes that what, plus 4x? And we want the parabola for values greater than 2. I think that was a plus. Sometimes some of these little marks disappear. All right. All right, so it's asking us, is this function continuous for all x from 1 to infinity? So it's just basically saying at the break of 2, at the break where it goes from one graph to another, okay, are the y values the same? Is the graph matching up? Because we know this graph by itself is continuous, and we know a parabola is continuous, so it's well behaved. So let's just do the 3-part continuity test. It's h. H of 2. Well, let's see, 2 belongs to the top piece, so let me put 2 in where I see x, so 2 minus 1 is 1, 4. Let's find the left limit. The limit as x approaches 2 from the left. 2 from the left is going to be the absolute value piece. So just doing the same thing we did in part 1. It's 4. If I'm approaching 2 from the right, I'm on the bottom piece here, which is this quadratic. All right, evaluating the bottom piece. At 2, we're going to get 2 squared, 4, -4. This becomes -4 plus 8. Plus 8 is 4. Okay, so if I can squeeze it in here, I'm going to do my stack of 3 dots, and I'm going to say, okay, therefore the limit exists, and it's 4 as x approaches 2. Okay, and I think we can clearly see everything's working out to be 4, so for the third part, we're just going to state, okay, that part 1 and part 2 are equal. So the functional value at 2 is equal to the limit as x approaches 2. And visually, that just means we don't have a point discontinuity. That the limit's going into the point at x equals 2. Okay, so I'm going to do 3 more problems on this worksheet, so that's going to require another video. So I'm going to stop here and we'll do number 5 in the next video.